In this video, we're going to do a quick review of the states of matter and how the particles in the states of matter will differ from each other. For example, if you're solid, liquid, gas, how do your particles differ? We're going to take a look at the particle theory of matter to explain behavior of different states of matter. And then we're going to jump into what's called the kinetic molecular theory to explain how gases behave, because this unit is primarily focusing on gases. So we're looking at stoichiometry in gases, gas laws, gas formulas, and to understand gases, we need to understand all these theories, particle theory, and specifically the kinetic molecular theory. So your first little task is to make sure that you preview the material to review the different properties of the different states of matter. As you know, there's three main states of matter: solid, liquid, and gas. Of course, there's plasma, but we focus on solid, liquid, and gas in chemistry. And so you should know the properties. For example, solids have a constant shape, so their shape remains the same, whereas liquids, their shape varies. Same thing with gases. Solids' volume stays the same. They're also almost incompressible. And liquids have that in common. However, with gases, the variable is volume is variable. It means it could change based on the container, and then they're also compressible. So you can squeeze them using a force into a smaller volume. You can compress them. And then you can take a look at how the particles differ from each other. So you can take a look at the organization of the particles, how in gases they're less organized, they move around faster, there's random motion. In liquids, they're a little bit more organized and they don't move around as fast and they just slide past each other. And in solids, they're more organized. They do still move. They have a vibrational motion instead in a fixed position. So that's a brief overview of the characteristics of the states of matter by looking at their properties based on their particles, how the particles arrange. And there's a great video here that goes over that in a bit more detail if you'd like a greater understanding. So we're going to study what's called the particle theory of matter. We abbreviate that to PTM. And that just basically it's a theory used to describe matter. And it essentially explains the behavior of matter, solids, liquids, and gases based on their particles. So the particle theory of matter has a few points that you need to know. First of all, when you look at matter, all matter is made up of these tiny particles. And then all the particles of a given substance are going to be the same. So for example, if you're looking at water, all the particles of water are all H2O particles. And different substances are made up of different particles. So H2O is made up of H2O. And then let's say carbon dioxide, dry ice, a chunk of it's made up of CO2 particles. So particles of the same substance are the same, and then particles of different substances will differ from each other. What's important to understand as well is that when you're studying these particles, there's always attractive forces that exist between them. So they are attracted to each other, and there's always space between the particles. It doesn't matter if you have liquid, gas, or solid, you're always going to have space in between the particles as well. And the particles are always moving, even in a solid. So just keep that in mind. And a neat thing is you can actually go from one state of matter to the other by adding energy. So for example, if I'm a solid, I can add some energy to make the particles move faster and they'll become a liquid. Then I can add energy to make the particles move even faster and eventually they'll evaporate and become a gas. So you can convert between the three states of matter. When you do that, the particles themselves stay the same, their identity. However, the amount of energy they contain and how much they're moving and their organization, that will change. And we'll see that in more detail shortly. So as we mentioned, there's three different states of matter. Solid, liquid, and gas are the main ones we focus on. And they differ in terms of their space, attraction, volume, motion, shape, and compressibility. And we'll see how they all compare. Before you start the lesson, it's a great idea to participate in this Jamboard here. You can just open it up and make a copy and just add ideas to it to see what you remember from the states of matter. You'll be surprised to notice that you actually remember quite a bit if you just think about it a little bit. So we'll talk about attraction first. How do these different states of matter differ in terms of attraction? So when we look at the attraction, you should be able to arrange these from weakest attraction to strongest attraction and vice versa. So the weakest attraction exists within the gases. The particles are not as attracted to each other as they are in other states. The strongest attraction is solids, and then liquids are somewhere in between. Those ones there. Another area where they differ is the space. So when we look at space, gases have the most space between them. Solids have the least space between the particles. And then liquids are again somewhere in between. Another area they differ is the motion. And very similarly to the previous characteristics or properties, gases experience the most motion and most varied motion. Solids still experience motion, but just not as much as the gases or the liquids. And liquids, again, are somewhere in between with different motion, but more than solids. So just a little bit more on motion so you understand how the motion differs from solid to liquid to gas. So when it comes to solids, they are still moving, but they move in a fixed position. They're just kind of sitting there vibrating, almost like they're shivering. So they're still moving, but a vibrational motion, we call it. There's also something called a rotational motion. And a rotational motion is when the particles sort of spin in place. So it's not that they're there just vibrating in one spot, but they're also spinning in place. So essentially, you'll see this for liquids. You'll also see it for gases. But liquids have this rotational motion in addition to some vibrational motion. As you can see, vibrational motion is experienced by all states of matter, gases, liquids, and solids. But for solids, it's really the main sort of motion. When it comes to rotational motion, you're going to see that in gases and liquids, and very, very, very small amounts in solid, almost non-existent. So very, very limited in solid. So in other words, when it comes to the liquids will experience rotational and vibrational. Solids will primarily only experience vibrational. Now, gases, they'll experience this vibrational, they'll experience the rotational, but gases will also experience a translational motion, which is where they actually move through space. So this particle will go from here to here, from here to here, from there to there. The other particles aren't doing that, but these ones here are. So gases kind of do this rotational and vibrational and moving all at the same time. So it's a very sort of random motion occurring. So gases experience the most. They can experience translational, rotational, and vibrational. Liquids will experience rotational and vibrational. And then solids experience only vibrational with some limited, very limited rotational motion. So this is just a little visual of what the different types of motion look like. So if you look at vibrational, they're sitting in one spot. And for example, here you can have maybe the bonds bending, the bonds maybe stretching, or stretching to one side. Here they're stretching both sides. Here it's only one side, so there's stretching or bending while the particles just stay in one spot. And this is really the only thing that solids are capable of, and all the other particles can do this as well. In terms of rotational motion, you have the particles in spot, but is actually spinning around on its axis, for example. So we have going this way or going the other way. But the point is that it's spinning around in space in addition to vibration. So liquids, they're able to do the vibrational motion and the rotational motion. And again, this is sort of like tumbling end over end. So spinning around in space. And then we also have translational motion, where you're actually moving from one place to another. And so gases experience this. Gases can do their vibration, they can do the rotational, and they can do the translational. So gases have the most type of motion available to them. And if you want to see the molecular motions in more detail, you can watch this great TED Talk here about how particles move. And you can see vibrational, you can see the translational, and you can also see the rotational in action. Great little visual. So let's go take a look at the volume, how these substances differ in terms of volume. Let's assume these are all the same substances and we're going from gas to liquid to solid. Notice that gases are going to have the greater volume, liquid smaller, and then solid even smaller, but this will vary. So this is the important part about the volume. We're talking about whether they have a variable or fixed volume. We can also say definite or no definite volume. In other words, a solid, if I have this little block here, whether it's in this container or in a container of a different shape, the volume will stay the same. So we say it's a fixed volume. It's not going to spread to take up the space in the container. Unless I force it to in some way, it won't do that. So solids have a fixed volume. Liquids as well. If I take this and I put it into a larger container, the liquid's not going to expand and go into the larger container. It's just going to take up the same amount of volume, the same amount of space. However, gases, if you look at them, gases, they don't have a fixed volume. So if I take this gas here and put it in a very large container, all the particles will spread out in order to take up all the space of that larger container. They'll take up the space of the entire room if they can. So they'll spread out to do that. And so gases, they do not have a fixed volume, whereas solids and liquids do have a fixed volume, or we see a definite volume and then not a definite volume. In terms of shape, it's the same idea. So solids, their shape will stay the same regardless of what container you put them in, unless you force them in some way and break them up. But in reality, they're not going to do that on their own. So their shape is a fixed or definite shape. Liquids, on the other hand, it's a little bit different. They can take up the shape of their container. So if I put it in a heart-shaped container or a beaker, they'll take up the shape of the container they're in. So they don't really have a definite shape. Their shape is not fixed. They still will maintain the same volume, so they won't expand to fill up the container, but they'll still take some shapes of the curvature of the different container they're in. And gases, same idea. They not only will fill up the entire container, but they'll take up the shape of the container as well. So they don't have a fixed shape. They'll change it based on their environment, whereas solids won't. And then we come to the idea of compressibility, basically how closely you can squeeze these particles together. And so what I want you to get is that for gases, the particles are so far apart, you can actually take a little piston and push the particles closer together. So you can actually compress gases very, very well. On the other hand, liquids and solids, their particles are already so close together, we say they're essentially incompressible. So liquids are essentially incompressible, and then solids are also incompressible. But gases are compressible. So you cannot essentially squish liquids and squish solids into their smaller space. So just to show you those concepts we just learned there, if I take a rock from this container and put it here, the shape stays the same, the volume stays the same, it doesn't take up the shape of the new container. For the liquid, just to show you, if I had 1,000 mils over here and I pour the 1,000 mils into this different shaped container, yes, the liquid will take up a different shape, but it still only reaches 1,000 mil mark in this area here. It's not going to have a different volume. So just like the solids, the liquids have a definite volume, but they are able to take up the shape of their container, so their shape is variable. And then for gases, if I take gas from this container and put it here, the gas particles will basically take up the shape of the container and also spread out to take up the entire space of the container. So they have a variable shape, but also a variable volume if you're a gas. And so this is a summary of the different types of matter that we've seen. We saw that they're different in terms of their attraction, their organization, their types of motion. So different in those different aspects there. You'll notice that in this table it says that liquids can experience translational. It'll be very, very limited translational motion for liquids. That's really primarily reserved to gases. Attraction, strongest in solids, weakest in gases, in between for liquids. Organization, super organized for solids, not so much organized for gases, and then somewhere in between for liquids. So this table here is a great table that connects the particle theory of matter to different substances and different compounds. So you'll notice that we have ionic compounds, polar molecular compounds or polar covalent compounds, and non-polar compounds as well. And so when you have ionic compounds, because they have such strong ionic attractions between them, electrostatic forces, usually the ionic compounds will be solid at room temperature. Whereas if you have, let's say, non-polar molecules that have very weak intermolecular forces, they can exist as solid and liquid, but you can also find them existing as gases more frequently, especially when they're small, just because the forces are so weak between them and can't hold the particles together. And then for polar molecules, same thing. You'll have a variety, solid, liquid, or gas, but typically you'll find a lot of solids and liquids for these polar molecules because they can have some strong attractions between them, especially if they're polar. They have their dipole-dipole, hydrogen bonding, so on and so forth. But the main idea I want you to get is that the more forces there are in between particles of a substance, the more likely you can be in what's called a condensed state. You can be solid or you can be liquid. But if you have a nonpolar molecule that's very small with very few attractions and very weak ones, then they're likely to be a gas because it's easy to break those little weak interactions that exist between them. And again, when you're changing state, you're focusing on these intermolecular forces over here. So that's just a summary of the connection between the intermolecular forces you've seen before and the states of matter that you might sometimes see. So on that line of states of matter, you do need to know the transformation that can occur from one state to another by adding or removing energy, and you should know what they're called. So for example, if you have some solid and you add energy to it to heat it up, it will melt and become a liquid. If you add energy to the liquid, enough energy, the particles increase in their speed and they will evaporate. It's evaporation or vaporization and become a gas. And then you can go the other way around as well. So for example, if you remove energy from gases, they will go through condensation and become liquids again, like rain. And then if you remove energy from liquids, well, they will become solids. Like when you put water in a freezer, it becomes solid water. It becomes ice, and that's called freezing. So you can go essentially add energy or remove energy to change between the states of matter. There's one more really cool state of matter that's called sublimation. And sublimation is when essentially you go from solid to gas without actually going to liquid. And so a really cool example of that is dry ice, which is frozen carbon dioxide. It's so cold, it's negative 78 degrees. When you take it out of its special fridge and bring it into the room temperature, it immediately becomes a gas as opposed to becoming a liquid. So sublimation is when you go from a solid to a gas, and then you skip the liquid state. Now there is one more term I didn't mention. I'm just going to add it here by typing it in. So sublimation is when you change state from solid to gas directly. And then, although I said sublimation here, in reality, a better term for this, deposition. Let's add that there. So deposition is a change of state from gas to solid directly. So in a way, you're skipping the liquid state, and then over here too, directly. You're skipping the liquid state. So that's called deposition. And there's a great demo over here that shows some of the change in states, and you can even see dry ice being demoed over here. It's a really, really cool demonstration. If you get your hands on dry ice, it's really neat to see. But those are the different states, change of states that you should know. And how do you do them? By essentially adding or removing energy to change how the particles are behaving. So if you have a solid and you add energy, that speeds up the particles. It gives them more motion, more space between them, less attraction, and they become a liquid. If you give energy to the liquid, it increases the space between them, gives them more motion. They're moving faster, and they become a gas. And then essentially going the other way around, it's the same idea, just in reverse. So you should be able to explain different phenomena using the particle theory of matter. So for example, if I ask you to explain why a solid melts when you heat it, well, I want you to talk about its particles. So I want you to tell me that you're adding energy to the particles of the solid. And when you add energy to the particles of the solid, it's going to decrease the attraction. It's going to increase the space between them and also the motion, and they'll be converted into liquids as a result of that. So there's attractive forces. The particles are always moving. When you add energy, the attractive forces are going to essentially decrease, and then that's going to lead to your substance becoming a liquid. So our main focus now, though, going forward is going to be on the gas state. So we're just going to summarize the gas state over here. And then after that, we're going to go to our handout and fill in information about what we learned so far. We'll complete the handout for that segment, and we'll come back and look at the gas state in more detail, along with the kinetic molecular theory. So just a reminder, though, for gases, they do take up the shape and volume of the container. They're highly compressible because they have a very low density. They flow very easily. So they have low viscosity. They mix with other gases. They're miscible with other gases. That means they mix. Their motion is very random. They have the the vibrational, the rotational, the translational, kind of all together at the same time. That's called Brownian motion, actually. It's kind of interesting. You can watch a video about it over here if you want more details. And also another interesting thing about gases is that they will expand as their temperature increases. And so we'll see that in some more detail shortly. Let's go to our handout to fill out what we learned about when it comes to the particle theory of matter. And then afterwards, we'll go and study gases in more detail. So let's see what we remember. This is a good exercise to see if you were paying attention. So we saw that there's a particle theory of matter, which is a theory used to explain the behavior of different states of matter. And in that particle theory, there's 5 main points. We saw that, first of all matter is made up of these tiny little things called particles. That's right. All particles of one substance are the same, and different substances have different particles. There are attractive forces between particles. There are space. There's space between particles. And the particles are always in motion. And we saw that there's 3 main states of matter. One of them is solid. One of them is liquid. And one of them is gas. And the states of matter, their particles differ on a variety of aspects, and you should be able to explain which one is the highest and lowest in terms of these different properties here. So if you look at attractive forces, the solids have the highest attractive force, so strongest or greatest attractive force. The liquids are somewhere in between, and then gases have the smallest attractive forces in between the particles. For amount of space, solids have the smallest, gases have the greatest, and then liquids somewhere in between. For the motion of molecules, gases have the greatest, and then solids have the smallest, with liquids again somewhere in between. Volume, we have to see if they have a definite or not a definite volume. So for solids, they do have a definite volume or fixed volume. So you could say definite or fixed. Same thing with liquids, they do have a fixed volume. Whereas for gases, it's not definite. We might sometimes call that variable volume. In terms of shape, the solids have a definite or fixed shape. They maintain the same shape regardless of their container. Liquids, they actually don't have a definite shape. It's a variable shape, variable. And then same thing with gases. It's not a definite shape. It is a variable shape. And lastly, when it comes to compressibility, we essentially saw that gases are the most compressible, and then solids are the least compressible. But we say that solids and liquids are basically almost incompressible. Solids are not compressible, liquids are not compressible, but if we had to give them a little degree of compressibility, we'd say solids would be the least, liquids would be still very small, but somewhere in between, so essentially incompressible, and then gases are the most compressible because they have low density. You can actually squeeze them close together since their particles have so much space between them. We also saw different motions of molecules and particles. And so we saw vibrational motion, which is the only thing that solids are capable of, but all the other particles like gases and liquid particles, they can do that as well. It's just solids is the only thing they can do with some limited rotational. And so again, that's simply moving in one spot, like vibrating back and forth or bending or stretching back and forth in one place. We saw rotational, which is tumbling or sort of spinning or rotating around an axis, still in one space. And essentially, we know that the liquids are able to vibrate and rotate as well. Some liquids do have some limited translational motion, but it's very limited. And then we saw translational motion primarily in gases, where you move from one position to another. So you actually move from one place to another. And that's found in gases. Gases are able to do the vibrational stuff, the rotational stuff, and the translational stuff, so they have the most motion overall. And there's a video that you can watch to see what those different types of motions look like. Then we arrived at the point where we saw that you can actually find a connection between the forces that exist between different types of particles and the state that they're found at room temperature. And so the idea is that if you have a very strong forces between your particles, then you're more likely to be solid at room temperature. So you can have them exist as, for example, ionic compounds that has very strong attractions of ions. And so usually we say they're solid at room temperature. You can melt them by adding energy, of course, but they're typically solid at room temperature. Nonpolar substances have very, very weak intermolecular forces. Remember, usually the LDF. And so since they have very weak intermolecular forces, it's very easy to split the particles apart and to separate them. And so you could have them exist as gases, especially the very small ones. That's not to say they don't exist as liquids or solids. They do, especially when they get bigger and there's more LDF. But the very small ones with very weak forces exist as gases. And polar substances, they do contain dipoles, and they can do hydrogen bonding as well. And because they have stronger forces, yes, they can exist as gases, but a lot of them can exist as liquid or solid as well. So essentially, any of these can exist as liquid, solid, depending on the temperature, gas, depending on the temperature. It's just that when you have the nonpolar ones, the intermolecular forces are so weak, you'll find more of the small ones that are actually gas at room temperature. And then for polar ones are stronger forces. So yes, some can be gases at room temperature, but you're more likely to find some solids and liquids compared to nonpolar substances, as long as they're similar sizes. And for ionic, the attraction is so strong between the ions, the electrostatic attraction, that typically ionic compounds, you're going to find them as solid at room temperature as opposed to liquid and gas. You really need to heat these up because these have a really high boiling point and melting point to get them as liquids. And that was just kind of a little overview and connection that we made with Unit 1 earlier. The last main point that we saw is the changes of state. And so we saw there's different changes of state that can occur. You can have melting, where you change state from solid to liquid. We also saw that you can change your state from liquid to solid, so that's essentially freezing. We saw you can go from liquid to gas, which is evaporation. The other way around as well, from gas to liquid. So like raining, which is condensation. And then sublimation is when you change from a solid to a gas. And that's directly. So you basically skip the liquid step. And we added one more, which is deposition. And that's when you go from a gas to solid directly. So essentially you're skipping the step of liquid. And so the example we saw for sublimation, which is not a very common example that you're used to seeing, is dry ice. So there's a video of that in the slide deck, and you can watch that to get some good demonstration there. But what I do want you to know is that the reason that these happen is because you're changing the amount of kinetic energy in the particles. If you add energy, for example, you can go from solid to liquid, because what you're doing is you're adding energy to the solid. The particles are starting to move around more because there's less attraction between them. The space between them can increase. They have more variety in their motion, and they're becoming a liquid as a result of that. So all these changes of state can be explained by the different characteristics of the particles within them, and you basically do the changes of state by either adding or removing energy. And I know that was a little bit quick, but you've seen that quite a few times. Just make sure you do a brief overview of it so that you understand it. And then lastly, we said that you should be able to answer questions related to particle theory or related to behavior of matter, and use particle theory to explain that behavior. So if I ask you to explain why something melts, or maybe why something evaporates, can you talk about the fact that the particles are gaining energy, for example, when something melts? You're weakening the attraction between the particles, increasing the space, giving them more motion, and as a result of that increased space, weaker attraction, and greater motion, they turn into a liquid. And so you explain the observation, the behavior, using ideas behind the particle theory of matter. So in the next video, we're going to go and focus on gases. We're going to talk about the properties of the gas state and the kinetic molecular theory and how we use that in order to understand gases in experiments for chemistry.